Hey students, today we've got section 5.4, exponential growth and compound interest. A little bit of a break today as this lesson has 3 parts, and 2 of the parts you've already learned about. We're just relating it now to investments and growth of money. So compounding annually, you put in your money and it earns interest every year. That's an equation that we've already worked with. Compounding continuously, so you have your money invested and it continuously, every millisecond is growing, earning interest. That's also an equation we've already used, but here is our new equation, compounding periodically. So this is the one new equation that we got to talk about and learn today. So let's go through some examples. So future value of an investment with annual compounding. All right, we've got the A equals P times 1 plus R to the T power formula. A is the amount, the value. P is the principal or initial amount. 1 is 1 plus R. R is the rate as a decimal. And T is time in years. So here's an example problem. An investment offers an average annual return of 3.2%. If you invest $600, how much will your investment be worth in 10 years? Okay, well, we plug in what we know into that equation, into our calculator. Okay, so 600 is P times 1 plus our interest rate as a decimal, 3.2% as a decimal, 0.032. All in parentheses, raised to the T power, and T is years. Okay, so we're doing it for 10 years. Plug that into our calculator and hit enter, and we get $822 and about 14 cents. So this is kind of nothing new. It's the equation we've used before. Then there's compounding continuously. So not waiting till the end of the year, compounding every millisecond. This is where this goofy number E comes from. By the way, there'll be an extra credit homework video if you watch kind of where this the history of this number. I've got it loaded up on an Edpuzzle, so a chance to get an extra credit point if you watch it. So suppose $600, same as before, is invested at 3.2%, same interest rate for 10 years, compounded continuously. What will it be worth in, 10 years? So using that equation, 600 times E raised to the RT power. R is our rate, 0.032, 3.2% is decimal, times 10. And we should get $826 and about 28 cents. And if you compare that to what we had when we compounded yearly, you can see that we make about $4 more when we compound continuously. Now, not everything in the real world is annually or continuously. There are times when maybe it's credit cards or your banks or your mortgages where things get compounded periodically. Monthly is very common, and so we have a different equation. We have A equals P times 1 plus R over N to the NT power, where N is the number of times you're compounding per year. So if we're compounding monthly, N is 12. If we're compounding weekly, N is 52. If we're compounding quarterly, N is 4. If we're compounding biannually or twice a year, N is 2. If we're compounding every day, N is 365. So let's show you an example problem. You might have guessed it. We're going back to the $600 for 10 years at 3.2%. But now, instead of continuously or annually, we're going to compound monthly. So every month. So our N is going to be 12. So what does that look like? 600 times 1 plus R, 0.032, divided by 12. So our interest rate is divided up into 12 equal parts, one for each month, raised to the power of 12 times 10, because we're compounding 12 times a year for 10 years. So 12 times 10, we're compounding 120 times. And you can see we get 825.92, which is slightly less than if we compounded continuously. And maybe you're thinking in your head, can we get any larger than compounding continuously? Is this the biggest we can get? And the answer is no, we cannot. Compounding continuously is the largest possible. We're compounding every nanosecond, so cannot compound any faster or any more times. All right, let's have you try a few problems on your own. So here's our first problem to try on your own. Comparing the three. Let's say you have $100,000 and you invest it and it grows at a rate at 15% per year. How much money will you have in 10 years if you are compounding annually, continuously, or monthly? All right, see if you can figure that out. All right, so here's the answers. Hope they match up with what you got. You can pause right here if you need to go over them a little bit, take a little more time to go over them, but we're going to move on to the next problem. So again, try the next problem on your own. It says if $100,000 is invested and grows at a rate of 15% each year, how long will it take to be worth $200,000 if you're compounding monthly? Okay, so this is a bit of a challenge problem. You could do it algebraically or graphically. So I set up the equation. We want to know when this periodic compounding is going to be equal to 200,000. So we started at 100,000, going to be equal to 200,000. We got our 15% as a decimal. We're dividing by 12 because we're compounding monthly. And we're multiplying by 12 for the same reason. These are n's. So first thing we want to do is we want to solve for t. So we try to do everything we can to get t by itself. And we got a lot of steps here if we're going to do it algebraically. First step, divide by 100,000 on both sides. So we can cancel it out right here. That's going to leave us with 200,000 divided by 100,000, which is just 2. So we've got 2 is equal to everything that was in that parenthesis to the 12t power. Now, something we should remember from our exponent rules is power to a power is something that we can separate. So this whole thing in red is a number we can plug into our calculator and just whatever it is, raise it to the power of t. So just power to a power is the same thing as multiplying exponents. So I plugged this into my calculator and I got this number 1.1607. which I'm going to round to about 1.161. So 2 is equal to, is about equal to 1.161 to the t power. So there's t, and we want to solve for it. How do we do that? We take the log of both sides. So log of 2 is equal to log of 1.161 to the t. Now we can use our log rules and bring t down. You can bring that down in front. So now we got log 2 is equal to t times log of 1.161. And now we just do algebra. Divide both sides by log of 1.161. So t is equal to log of 2 over log of 1.161. And we can plug that into our calculator. And we get 4.6432, or about 4.64 years. Now, if you don't like the algebra method, we could use our graphing calculator. So our Y1 is just our initial investment compounding monthly formula. Instead of t, I've got x. And then we want to know when it doubled, how long to double to get to 200,000. And here's how I set up my window so that I could see that. X min to -2, X max at 10. And I did a Y max of 300,000 because we want to see where it makes 200,000, so we might as well go a little bit above. All right, so we can see here's the exponential growth compounding monthly. Here's the flat line, 200,000. Second, trace, number 5, intersect, enter, 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 and we get 4.649. slight difference in answers because this would round to 4.65. That's because of when I had to round the 1.161, slightly rounded. All right, now that was a challenge problem, so a little bit higher level. Homework is the quizzes. Ask questions if you got them. There's that extra credit thing on there too. Bye.